Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. Today my lecture on Chemical Engineering Thermodynamics 1. This is lecture 4. In the previous lecture we have discussed about equilibrium state and the phase rule and the examples of the equilibrium states, the mechanical and the thermal, and the phase rule examples of phase rule. For the triple point, what will be the degree of freedom we have discussed, and the reversible and irreversible process with the example of its. So these things, these two topics we have discussed: the equilibrium, phase rules, and the reversibility and irreversibility of the process, and the examples of it. So this is the plot how the irreversible or irreversible process happens, and we have already discussed about the Gibbs and the equilibrium states we have, and he is the Gibbs who is given the first time the phase rule for non-reacting system. Now in today's lecture we will discuss about internal energy. So what is the internal energy, and how you can relate with the first law of thermodynamics for cyclic process, and we will know about the what is the first law of thermodynamics and the first law of thermodynamics for non-cyclic non-flow process. So these three topics today we will discuss in our lecture. So now we will start with the Joule experiments. So the Joule experiment, in the present day the concept of heat developed following crucial experiment carried out in the 1840 by James P. Joule. So he is the man. In the most famous series of measurement, he placed known amount of water, oil or mercury in an insulated container and agitated the fluid with a rotating stirrer. So like this is a setup. So the amount of work done on the fluid by the stirrer and the resulting temperature changes of the fluid were accurately and precisely measured. Joule shows that for each fluid, a fixed amount of work per unit mass was required for each degree of temperature rise caused by stirring, and that the original temperature of the fluid was restored by the transfer of heat through simple contact with a cooler object. These experiments demonstrated the existence of a quantitative relationship between the work and heat, thereby showed by the heat is a form of energy. Okay. So the internal energy. So if you will see, this is a pressure versus volume graph, and internal energy is a state function. So that thing we will read now, we will discuss now. The internal energy of a substance does not include energy that it may possess as a result of its gross position or movement as whole. Rather, it refers to energy of the molecules comprising the substance. Because of their ceaseless motion, all molecules possess kinetic energy of translation, motion through space, except for monoatomic substance. They also possess kinetic energy of rotation and of internal vibrations. The addition of heat of a substance increase molecular motion and thus causes as increase the internal energy of the substance. So it is a molecular based molecular behavior. In the molecules level, the internal energy generally stored. Work done on a substance can have the same effect as shown by the Joule. That experience we have shown. The internal energy of a substance also includes the potential energy associated with the intermolecular forces. So these forces, intermolecular forces, which are non-bonding forces generally we called, and that associated with this internal energy. In the molecular dynamics, generally we calculate the internal energy in terms of how the force is acting on it. The molecules attract or repel one another, or potential energy stored through these interactions, just as a potential energy of a configuration is stored in a compressed or stretching spring. On a submolecular scale, energy is associated with the interaction of electrons and nuclei of atoms. So on a which includes the energy of chemical bonds and the whole atoms together as molecule. So the interaction between the atoms, it is also dependent on the energies. This energy is named as internal to distinguish it from the kinetic and potential energy associated with the substance because of its macroscopic position, configuration or motion, which can be through of an external form of energy. Internal energy has no concise thermodynamic definition. It is a thermodynamics primitive. It can not be directly measured. There are no internal energy meter. For now we will discuss about what is the first law of thermodynamics, how you will internal energy calculate by the first law of thermodynamics, and what this first law says. The idea of designing an engine that would produce mechanical work continuously without drawing energy from external source and without undergoing a changes had been great fascination for scientists and engineers. So the failure to construct such machine, which is called perpetual motion machine, forms the basis of for the law of conservation of energy, which is first time introduced by Helmholtz in 1847. The fundamental implication of this law is that although energy may be converted from one form to another, it cannot be created or destroyed. So this is the best example of perpetual motion machine, and he is Helmholtz. Whenever a quality of one form of energy is produced, an exactly equivalent amount of another kind must be used up. When the law of conservation of energy was proposed, heat was not considered to be form of energy. It was a series of experiments conducted by the Joule between 1843 and 1847 that established heat as a form of energy. A known quantity of water taken in an insulated container was agitated by means of paddle wheels. The resulting temperature rise are noted. It was found that exact proportionality exists between the amount of work expended on the water and the rise in the temperature. The same proportionality was obtained by the following difference method of transform work into the heat. Now in the next slide we will discuss the same proportion. The mechanical work was converted to electricity, and the electric current was passes through coils immersed in water. It will heat a gas confined in a cylinder immersed in a water was compressed mechanically. the two metal pieces immersed in a water were rubbed against each other by mechanical work, so heat is generated. So these are the examples which suggest that heat is also an important role. The recognition that heat and internal energy are forms of energy leads to their inclusion in the law of conservation of energy. Along with work, potential energy and kinetic energy, and its law came to know as first law of thermodynamics. So there is a universal truth that the energy of the universe is conserved. So the first law say that so there is a change in the system plus the change in the energy of the surroundings will equal to the zero. So this is the first law of thermodynamics. So the first law of thermodynamics: for a cyclic process, consider a static system and undergoing a cycle of changes. Work is done on the system by force acting from surrounding, or vice versa. Heat is transferred between system and the surroundings during the process. Then, according to the first law of thermodynamics, the algebraic summation of all work effect exactly equal to the summation of all heat effects. So you let Q denotes the heat added to the system and W the work done by the system. Q is negative then when the heat is rejected by the system, and if W is negative when the work is done on the system, and if both are measured in constituent units, so you can write like this: W summation of W equal to summation of Q. If the unit chosen for heat and work are different, the above equation can be written as, so there is another terms will be, you can write this is a constant, you can write, and the J is a mechanical equivalent of heat if the work is mechanical, and electrical equivalent of heat if the work is electrical. The first law of thermodynamics for non-flow process. The first law of thermodynamics requires that the change in the total energy of the system be compensated by an equal but opposite change in the total energy of the surrounding, so that there is a no net change in the energy in the process. The change in the total energy of the surrounding occurs only through the exchange of heat or work with the surroundings. So this thing we have already discussed, that the total energy of system which is equal to the total energy of surroundings, and the surrounding energy is the work and heat of with the system. When the changes of the total energy of the surroundings, which we will denote like this, must be equal to the energy transferred to or from it as heat and work. Since Q is the heat transfer to the system and W is the work extracted from it during the process. So this is a equation, the surrounding energy of the surroundings, which is minus Q plus W, and for the closed system undergoing only changes in the kinetic, potential and internal energies, the total energy changes in the of the system is given by, so del E system, which is equal to del Ke plus del Pe plus del U. Okay, so this is a total energy of the system, which is the kinetic energy, internal energy and potential energy. So since del E system equal to del minus del E surroundings, we can combine equation 1 and 2. So when you will rearrange this equation, so you will get del K potential energy plus potential energy kinetic energy plus potential energy and internal energy, which is equal to Q minus W. In the above equation, the kinetic energy and potential energy denotes changes in the denotes. Okay, so the equation 3 means the total energy changes in a closed system is equal to the heat added to the system minus work done by the system. So these two terms will be negligible, then only the heat and work done will be remaining. For a steady state non-flow process in which there are no changes in kinetic energy and potential energy, the equation can be simplified. This equation for the non-flow system when there is no kinetic and potential energy. So del U equal to Q minus W. These other two terms are cancelled. So for remain differential changes in the thermodynamic state of a closed system will be del du equal to dq minus dw. Okay, so this is the differential form of first law of thermodynamics, and this is the internal energy you can calculate. Now we will discuss about some examples of the closed system. A system consisting of some fluid is stored in a tank. The rate of work done by on the system by stored is 2.25 horsepower. The heat generated due to stirring is dissipated to the surroundings. If the heat transfer to the surroundings is 3400 kilojoule per hour, determine the change in the internal energy. So how you will calculate this internal energy? So we know about that formula, internal energy equal to the the heat minus the work done. So the work done on the system can be obtained as so this work done you will change into the joule per second. So because it is given in the horsepower, so when the 2.25 horsepower, if you will multiply with this 745.7 this term, so you will get 1677.8825 joule per second. So this will be the work done which is given, and it is done by the stirrer. So heat transfer to the surroundings is which is given Q equal to 3400 kilojoule per hour. If you multiply with this, if you will change this into the joule per second, so that will be the, you have to multiply 103 divided by 10 to the power 3 divided by, it is 10 to the power 3 which is divided by 3600, so it will be 944.44 joule per second you will get it. So this is the heat, both are the these two quantities given, so you can easily calculate the internal energy. So that is del U Q minus W, so minus 944.44, so if you will put it, so you will get 733.381 joule per second. So this will be the internal change in internal energy you will get. So the internal energy of the system increase by this one in 1 second. So example 2, suppose iron filling are containing in a cylinder in an atmosphere of oxygen. It combines with oxygen according to the following reaction. So this is a iron and this is a oxygen. This is oxidized and this is iron oxide is forming. The pressure inside the cylinder is maintained by 101 kilopascal. The temperature is kept constant at 298 Kelvin by removing heat. For 2 mole iron reacted, calculated Q, W, heat, work done and internal energy given 831.08 kilojoule of heat is liberated in the process. So we have given this heat and the temperature and pressure we have given for the system, and we have to calculate the heat, work done and the internal energy for the process. So this how you will solve this question. So the heat liberated when the 2 mole iron reacts with oxygen, 3.5 oxygen, so you will get 831.08 10 to the power 3 joule energy, heat is liberated. So neglecting the volume occupied by the solid, the volume changes occupying the process is equal to the changes in the volume of oxygen. Assume ideal gas behavior for the gas. So we know the PV equal to nRT. So this is a well-known equation. So where del V is the volume change and del N is the increase the number of moles accompanying the reaction. Here del N equal to minus 1.5. So it is for oxygen. So work done by the system will be W equal to P del V, which is equal to del N RT. Okay, so we know about the moles, which is 1.5, R we know 8.314, and temperature is given, which is 298. So you will get it 3716.4, because we do not know the volume changes. So by this we can directly rearrange the equation and we can get the work done. So we know about the work and the heat. Now we can easily calculate the internal energy, which is del U equal to Q minus W. So this is the equation. If you will put these values in this equation, so you will get it minus 8827.364 10 to the power 3 joule. So this will be the change in the internal energy. So now we will discuss about the another example. Suppose a car riding downhill at a speed of 20 meter per second was applied brake when it was at a height of 30 meter vertically above the bottom of a hill. When the car comes to a halt at the bottom of the hill, how much energy as heat must be dissipated by the brake? If wind and other friction effects are negligible and car weight is 1400 kilograms. So it is very interesting example. So the first law of thermodynamics, we know about the del internal energy equal to the heat minus work done, and the kinetic energy, if there is a presence of kinetic energy plus potential energy. So the kinetic changes in the car respectively. The kinetic energy of the car is 1 by 2 mv square and potential energy mgz. So we know about the speed and the mass of the car, so we can easily calculate the kinetic energy. The kinetic energy and potential of the car when it comes to the stop at the bottom are both equals to 0. Therefore the changes the kinetic energy and potential are negative of their respective initial value. So the mass is the m is the mass and u is the velocity and z is elevation above the bottom of the hill. So the kinetic energy we can easily calculate 1 by 2 m we know the 1400 and u velocity we know it is speed the 20. So we can also calculate the potential energy. So we know the potential energy mgz. So height we know the z equal to this 30 meter and g is gravity 9.8 and this mass we already know. We can also calculate the potential energy by this equation. So it is 4.12 into 10 to the power 5 joule. Therefore therefore the heat will be dissipated if you will sum of these two, kinetic and potential energy. So you will get minus 2.8 plus 10 to the power 5 plus minus 4.12 into 10 to the power minus 5. You will get minus 6.92 into 10 to the power 5 joule. So this will be this much amount of heat is dissipated. In this case there will be the no internal energy, only this will equal to the there is a no work done and the internal energy, only Q equal to the potential and kinetic energy. So the heat dissipated by the brakes is this one. So now we will calculate and we will discuss another example of a system consisting of a gas confined in a cylinder is undergoing the following series of processes before it brought back to the initial conditions. Step 1, a constant pressure process when it receives 50 joule of work and gives up 25 joule of heat. Step 2, a constant volume process when it receives 75 joule of heat. And step 3, an adiabatic process. Not in adiabatic process there is a no heat exchange between system and surroundings. Determine the change in internal energy during each step and the work done during the adiabatic process. So now we will all the three steps we will do, and we will calculate the change in internal energy. So internal energy changes for the step can calculated as, so this is a graph which is given by this question. So the volume and process, there is a B, C, these are three different paths. So if we will calculate the internal energy for A to B, so there is a change in the volume, so the internal energy is 25, the heat is 25 and work done is 50, so you will get it 25 joule, which will be the internal energy during now we will calculate for the B to C. No work is done as it constant volume process. So when it is a constant, the changes in internal energy is, there is a no volume changes, so it will be del U equal to Q BC. So there is a no volume change, so 75 joule will be you will get. And when you will do for the C to A, so in adiabatic process, so QCA will be 0, there is a no heat dissipation, so you will get del U equal to minus WCA. For a cyclic process, the net changes in internal energy is 0. When you will sum up all these three energy, so that will be del U AB plus del U BC plus del U CA, which is equal to 0. So then you will get it 100 joule. So this will be the, therefore the work done during the adiabatic process from C to A will be the 100 joule. So this will be the internal energy or work done for the this adiabatic process. So in today's lecture we have discussed about the internal energy, the first law of thermodynamics for cyclic process, first law of thermodynamics for non-cyclic non-flow process, and how the James P. Joule and Helmholtz describe the first law, and the Joule's experiment they have done and explained the first law of thermodynamics. And this is a Joule experiment, and this is a perpetual machine which continuously work. So by these examples today, and we have also discussed some examples of this internal energy and the first law of thermodynamics. So in the next lecture we will discuss about enthalpy, constant volume and constant pressure, first law of thermodynamics for flow process, example of it, and heat capacity. So these topics we will discuss in the next lecture. So thank you very much. If you have any doubt related to this today lecture, so you can ask me, and this is my email ID chemicalsuniraj@gmail.com, and this is my website. Thank you very much.